In the next 40 minutes, I plan to break the record for how many times an individual can say the word modularization, and I appreciate you all sticking around for this momentous event. I've been at Instagram for just about a year now. I'm a member of the core client performance team, and we're responsible for the speed and efficiency of the Instagram app across devices around the globe. We build infrastructure that protects and improves app-wide metrics ranging from app size, startup time, and scroll performance, to name a few. In particular, I lead our app modularization efforts for the Android code base. So I'm here today to talk about how modularization, or detangling your dependency graph, can help unlock performance wins for both your product and your team. I'll be starting by talking about the primary performance risks we identified that motivated us to modularize our code base. And after that, I'll discuss the specific methodology we are using to manage our dependencies. Finally, I'll address some of the very real pain points we have encountered in trying to modularize and have it be the new norm at Instagram. So let me start with an overview of Instagram's scale to set the scene for why modularization is important to us. Our engineering team has grown significantly across 3 offices since last year. Besides adding a wealth of new feature functionality to the app, we've started to expand into a family of apps with the recently released IGTV. Finally, our user base continues to grow, and we just crossed the major threshold, hitting 1 billion monthly active people. This kind of growth is truly remarkable, but it can come with its downsides. A distributed set of engineering teams contributing to an expanding code base will inevitably lead to engineering challenges. Although we embrace our growth, we absolutely do not want to sacrifice the top-notch performance that Instagram is known for. This is a trade-off we are simply unwilling to make. So we had to figure out the best approach to ensure the health of our code base over time. Instagram's code base began as I imagine most Android apps do, with a main activity and not much else. It was likely a single screen with a single function, and I bet it was lightning fast. And like all code bases, it grew from there in an organic fashion when features like Explore and Video were added. New code and new features are inevitable when building an app, and often when building features, we need to rely on code that exists elsewhere in the code base. As engineers, we've all been there, benignly adding a dependency when you need just a bit of functionality that lives elsewhere. You could refactor it, you could move it into a common library, but it's just that one method you need, you likely say to yourself. Finally, you rationalize taking the shortcut with those famous last words, how bad could it be? And you push your changes. Like I said, we've all been there. But ultimately, every single interdependency that is introduced into a code base complicates it. And with every shortcut we take, what started as a beautifully simple dependency graph can become a gnarly, convoluted mess. I present Exhibit A. This is a graph I recently generated from our code base. I was trying to track down why a third-party library that was intended to be used by only one of our features traced back to 8 of our features. The reason is that dependencies from one feature will bleed into others over time. It's quite a tangled web we weave if we're not careful. So let's talk more concretely about what impact this tangled web can have and why it motivated us to start making changes. Let's talk about build times. What if every day, every engineer on your team added 1 new dependency to the code base? And hypothetically, what if each new dependency tacked on an additional 30 seconds of build time? How well would that go over with the rest of the team? Patience is most certainly a virtue, but it's not one that all engineers have, especially when it comes to build times. If engineers knew their choices had an explicit impact on build times, would they make those same choices? Or do you think each engineer would more carefully consider the absolute necessity of each dependency they add? I think they would, especially if it impacted their own workflow and that of their teammates. Now, you might be asking yourself, how could a single dependency add this much time to a build? But what is also often overlooked is the potential impact of transitive dependencies. we did some internal benchmarking to better understand how the size of our modules impacted build size. I doubt you'd be too surprised to hear that with more lines of code led to longer build times. But more importantly, we identified that bigger modules, ones that were thousands of lines of code, let us say, often rely on a much larger set of dependencies. Those dependencies in turn trigger a large ripple of other modules that then need to be rebuilt. Although an engineer may think they are only adding a single dependency, transitively they may be adding way more. If you envision the dependency graph as a tree, the build time scales with the height of this tree. In an ideal world, you want a simple dependency graph that gives a very flat build tree, one that continues to grow horizontally with new features without impacting build time. Now, they say that first impressions are everything, so let's talk about startup time. Instagram used to have a pretty simple feature set: feed, explore, profile, but now there are a lot more features. And with more features in code, we have to start thinking about the interdependencies between these features in the code base. When a user clicks on the app icon, the first thing that will appear is Instagram's main feed. Under the hood, it means that we load all the code for the main feed into memory. Is that all that gets loaded? Well, not necessarily. What if the main feed has dependencies to other features, like search and like profile? In that case, the code from both search and profile may also get loaded at start time, even though those features aren't even visible yet. Now, perhaps that's a trade-off we're willing to make because of our product design and how our features interoperate. But what happens as we start to add even more features, like stories, direct, save, shopping? We now have even more code potentially getting loaded in at cold start time, and our trade-off becomes that much greater. One of our users waiting that much longer to interact with the app. This continual increase to cold start is not scalable. Although the number of features in the entire app will continue to grow, the amount of features that can fit on the screen are bounded. So it's important to be very conscious of the dependencies between your features and to eliminate those that are not absolutely necessary. Another aspect of the app that continues to grow as we add more features is the size of the app. Instagram's APK is currently about 36 megabytes. It's not too bad given the large amount of functionality that exists in the app, but research continues to show that a smaller app is better for install rates. Google released Play Store research that shows that for every 6 megabyte increase to an APK size, there's a decrease in the install conversion rate by 1%. So how can modularization help with this? Well, we recognize that as our feature set grows, people will start to use different subsets of those features. Perhaps you're a business owner who's interested in checking the insights for your account. Perhaps you're a music lover who loves to go live while at concerts. We know that not every person will use every part of the app. So how could we be smarter about how we load individual features? By isolating features into their own modules behind a strict API, we can prevent engineers from creating dependencies between features, but also carve features out of the main APK. Well, why would we do that? Dynamic Features was announced at Google I/O this year. It's an API that allows users to download and install features on demand once they've already installed the base APK for their app. Therefore, the Play Store can contain a slimmer version of the APK with just the core functionality. More peripheral features can be downloaded dynamically as the user interacts with the app. In order to take full advantage of this API, your app must be broken up into smaller feature modules. A code base with lots of dependencies makes this difficult to achieve. Also difficult is trying to reduce app size after the fact. Therefore, optimizing your code base such that you can leverage an API like this is well worth the effort. It allows your team to add features without bloating your APK size. So to sum up our primary concerns, the scaling challenge we face at Instagram is that as the number of features in our app grows, we risk build times, cold start time, and app size growing at the same rate. It's clearly unsustainable. Continuing this way would cause our app to feel unusable on certain devices and would be a pain for our team to develop. Instead, the trend line we'd like to see would be something like this. The number of features in our app can grow linearly or maybe even exponentially, but we'd like to keep performance metrics pretty much flat so that we can continue to deliver a performant experience. Now that we've covered some of the motivating factors, it's time to delve into our approach. In general, app modularization is the process of separating code into well-encapsulated modules. Once we have these modules, we examine the cross-dependencies between them and try to trim the dependencies down so that each module has a small, cleanly defined interface. That module defines the small set of dependencies that are exposed outside of the module, and meanwhile, the actual implementation of the module remains only internally visible. So let's say we're trying to modularize this messaging feature. Inside the messaging directory, we have a few subcomponents like fragment, helper, and so on. Before modularization, there can exist a number of dependencies from other modules to these subcomponents. For example, you see that profile and search are depending on something specific inside of messaging. However, after modularization, that's no longer the case. We create interface and implementation directories. The interface directory hosts the module's external-facing API, and this is where we define what functionality will be available to external call sites. Alongside it, we have an impl directory. It contains all of the business logic for the feature module. This implementation code is only accessible and visible to the module itself. Therefore, we break any external dependencies to code that lies beyond the interface. And if we need analytics or the store to use the messaging helper, let us say, they must access it through the features interface. And because this interface doesn't contain all the business logic, it relies on a much smaller set of dependencies. Transitively, that is even fewer dependencies making their way into other features. So how do we go about achieving this? The first step is to co-locate all the relevant code for your feature into a single directory. I know this may sound like a simple thing, but you would be surprised. All too often, code base start with all fragments living in a single directory, all adapters living in another. It feels like the simplest way to organize a code base when you get started. However, rather than have generic categories at the top level, we wanted feature modules at the top level, and only the relevant fragments and adapters contained within them. On Instagram, we initially had a single large monolithic directory that held most of the product code. Breaking code out in this manner was a nightmare due to circular dependencies that existed. Luckily, we had some tools in place to make this easier, such as a script for analyzing the dependency tree to figure out what the leaves of the tree were and which would be easiest to move out. This allowed us to work in waves, first moving out the simple model and helper classes, which then made it easier to move out our controller and fragment classes that were way more complex. So let's say we've managed to move all of our feature code into a single feature-specific directory. The next step is to take a look at all of the dependencies that exist to this feature and trim them down. Resolving these incoming dependencies can be tricky, and there's no set of rules for how to best handle it. But I'd like to share some of the learnings we've had from tackling this on Instagram. First up, a common source of cross-feature dependencies that we've seen is a generic code living within feature modules. For example, imagine we have the follow button on the profile. When the feature was first built, the follow button was only relevant to the profile because that was the only place you could follow another person. It made sense to build the follow button as part of the profile. However, let's say we decide to show the follow button in the search module when you're looking up other people. What happens then is that we need to add a dependency from search to profile in order to reuse the code for the follow button. Code reuse is a good thing, but it's dangerous for cross-feature dependencies like this to exist because of all the downsides I mentioned earlier. So what's the right thing to do in this situation? Well, one way to solve this is a small, single functionality library for many other feature modules to depend on. Another common source of cross-feature dependencies comes from doing feature work too early. Here's an example. Imagine we are transitioning a person from the main feed to their profile after clicking the profile button. You can think of this navigation as defining the boundary between these two features. But one common thing we see is that before actually navigating to the profile, there's some work being done early to set up this transition. There could be something simple like analytics logging, or something more complex like an animation or checking the state of the profile beforehand. Because this work happens earlier, before the navigation to profile has occurred, it has caused a dependency from feed to profile. To resolve this, it's better to push the work for profile as late as possible until after the navigation occurs. So again, there's no one-size-fits-all answer to resolving these dependencies. In the end, after you're done modularizing, there should be a few key dependencies left per feature module. To make the decision on which dependencies should be kept, it's helpful to think of your app as a platform. The platform should be composed first of a set of feature-agnostic utilities. These utilities have very few dependencies and contain no feature-specific logic. Next, the platform has a set of features. On Instagram, these are feed, explore. Try to think of each of these features almost as apps that run on this profile. They shouldn't have any dependencies between them. Finally, your platform needs to provide some platform-level functionality. An example of this is navigation, so that users can navigate between different features. Another example is app-wide lifecycle callbacks. In Instagram's case, this is when a user logs in or switches accounts. Different features would want to register for these lifestyle callbacks so that they can handle any user-specific logic correctly. I'd like to highlight a new area of concern for our team. Instagram and the health of its code base has been our sole focus for some time. However, we have branched out into building a new standalone app, IGTV. If our code base was in fact structured the way I laid out in the previous slide, building IGTV probably could have been a lot easier. In an ideal world, our code base would have already been modularized, thus enabling us to cherry pick just a handful of components that we wanted to share between our apps. However, as the team embarked on building IGTV, we became acutely aware of how difficult that process would be in our current state. Once again, our interdependencies reared their ugly heads, and the IGTV team's progress was slowed by having to refactor and cut the ties for the features they needed. In some cases, they couldn't cut those ties easily and thus ended up pulling in more code into their app than they ultimately would have liked. Through modularization, we are hoping to minimize how much code is pulled into IGTV and ultimately to help them reduce their APK size. When sharing code between apps, you want to make sure that one app doesn't inherit another app's performance issues. So that covers the specific approach that we've chosen to modularize our code base. But there's still some rather large questions that remain unanswered. How can we modularize a code base into which new code is being pushed every day? How does modularization become the new norm across a set of engineering teams? And as you start to modularize, how do you prevent your dependency graph from becoming tangled once again? There is definitely no one-size-fits-all solution here, but I will discuss some of the strategies that we are using to address these questions. We created a small team of engineers dedicated to this effort that I have dubbed the Mod Squad. It's a team of Android and iOS engineers that are responsible for looking at the code base holistically, prioritizing the risks that we are facing, and building the initial infrastructure and prototypes to be used as example modules. New engineers will often look to the code base to figure out what precedents they ought to follow. Therefore, having a couple of examples to look at is a good start. But if the majority of the code base is not yet modularized, you'll need to do more. We've created a detailed wiki to explain the how, what, and why of modularization, and we use this documentation to enlist the help of our product engineers. We also plan to make it part of our new onboarding materials, which are currently in the works. If the code base itself does not reflect the best practices we are suggesting, then teaching those practices early on to new engineers is a great way to get the message out. Even those engineers that have been working on the team for a while can use a reminder. So I presented on this topic internally to all of our Android engineers. The mod squad alone could not do all the work that I'm suggesting. We needed to enlist the help of others, so we met with mobile engineers from 20+ product teams in the hope that we could federate this modularization work. Ultimately, these engineers understand their features the best. If we want to trim dependencies, they are the ones who best know why they are needed and how to manage them. The problem, of course, is that these engineers have their own work to do. They are responsible for building new features for people to love in the product, and we understand that. But the more features built that aren't modularized, the further we push out our finish line. Our federation requests were met with mixed responses. Some teams just didn't have the bandwidth to do this work. Some were able to allocate an engineer to our cause and have since modularized their features. They have helped us make significant progress toward our finish line. And another upside is that getting product engineers involved, they become ambassadors to our program. Not only would they protect the efforts they made to modularize their own features, but they become way more likely to suggest that others do the same. It's impossible for me alone to keep an eye on our entire code base. But with vigilant eyes scattered across product teams, we've been able to further our progress by having someone merely ask, hey, have you considered modularizing this? Sorry, that was late. Now, no matter how much we want modularization to stay top of mind, there really is no guarantee that it will. Deadlines loom and priorities shift. Therefore, we put some measures in place to try to conserve the progress we've made on modularization. We certainly don't want to prevent engineers from pushing new features, but we do want them to be mindful of the choices that they make and the impact it can have on the greater code base. As we have established some best practices for the code base, these become rules that we can enforce. We have introduced some friction into the development process by creating a few dependency tests that run on every diff. If an engineer is trying to include a new external dependency, or if a dependency is added to a place it really shouldn't be, we warn them. We ask that they either make some changes or notify our group as to why this new dependency is needed. Additionally, we have a system of alerts in place to help keep tabs on some of our metrics. They cover a range from number of methods being added, which mattered in particular when we were still a single DEX app, to the number of kilobytes being added to both our compressed and uncompressed APK size. We've established a variety of thresholds, and as new builds are posted as part of our continuous build system, alerts will fire if a diff has caused us to exceed any of those thresholds. When that happens, we can determine which build caused the regression and file a task assigned to the engineer that is responsible. We are building tools and infrastructure to make sure we can track progress across our various metrics, but also to help bring greater awareness to all of our engineers. In closing, I want to revisit this graph, which is essentially our North Star. Our hope is to allow the features in our app to grow while keeping our performance metrics mostly flat. That said, influencing engineering culture can be quite an uphill battle, but you have to start somewhere. If your code base is young or small enough that you can easily modularize, take the time, do it now. If not, then pick a place to start. Start with that first module, that first wiki, that first ambassador on your team. It might seem that moving a rock won't move the mountain, but even the smallest effort helps to establish a new norm. It's especially worth the effort when the new norm means a brighter future for your product and how it performs and for the people who love it. And so that's it.